Okay, we'll do another example of an eigenvalue problem. And here is the whole statement. The differential equation itself is just like the previous example we did, but the boundary conditions are a little different here. And here they are. The sum of the function itself and its derivative at the argument of 0 equals 0. And the function itself at x equals 1 is 0. So again, we have the same three cases where lambda is negative, exactly equal to 0, and positive. When it's negative, we'll call it minus alpha squared. Since it's on a finite extent here, x goes from 0 to 1. Use this version of it, quotient sinh. Because the derivative is involved, we're going to have to take the derivative. Here's the derivative of that solution. So let's look at this first boundary condition. Some of those two guys at the argument of 0. When x equals 0, cosh is 1 and sinh is 0. So this sum will just be a plus b alpha. That equals 0. So we have a relationship between the two arbitrary constants a and b, I'll call it. So a equals minus b alpha, which gives us this surviving solution that satisfies the equation and this first boundary condition. So now let's look at the second boundary condition and put in the value of 1 for x. So I'll have b times minus alpha cosh alpha plus sinh alpha. This all has to equal 0. Now here we get to a bit of a subtlety. Either b has to be 0 or what's in parentheses here has to be 0. So can this part ever be 0? That would mean alpha cosh alpha equals sinh alpha, or it would mean alpha equals tangent of alpha. Can that ever be true? Well, I'll get to that on the next chart. But actually, that can never be true, which forces us to set b to be 0, which means we end up with the trivial solution and we reject it. Well, let's look at this little relationship here. It was what was involved was tangent alpha. So this blue line is the tangent function. So think of two different functions. You know, if I call the argument theta, here's one function of theta, the tangent. The other is just theta itself. Think of it would just be a straight line with a slope of 1, just theta. Well, remember the slope of the tang is 1 at the argument of 0, but less than 1 everywhere else. So that where alpha equals tang alpha, there is no intersection of those two functions. That never happens. You can't have alpha equals tang alpha. What if you had this guy? Instead of just, the case we just did was this c equals 1. Alpha equals tang alpha. That never happens. But what if c is not 1? If c is greater than 1, greater than or equal to 1, you don't get a solution. Think of the second function, c alpha side, would be a straight line of slope c. If c is greater than or equal to 1, it never intersects this tangent. But if it's between 0 and 1, you're going to get exactly one solution, where the two sides here this function on the left and the function on the right where they intersect. So this C alpha, if C is between 0 and 1, go from here to somewhere there. Right? So where those lines intersect, that's where you would get a solution. So you can't always dismiss a solution that looks like this. But in this case, we did reject it because our C was 1. Sorry for the long explanation of that. So we reject that case. Let's finish this. It's kind of a long problem. So let's look at the exactly equal 0 case. Lambda equals 0. Here was the general solution. So we're going to need the derivative, which is just b. So that first boundary condition turns out to be just a plus b. That has to equal 0. So we have a relationship there. It says our surviving solution is this guy. So let's look at this solution at the second boundary condition where x equals 1. Well, there we get equals 0, no matter what. So a doesn't have to be 0. So a can be arbitrary. So we do not reject that case. So we get a eigenvalue of 0 with this corresponding eigenfunction. This case, we do not reject this second case. The third case, where lambda is positive. If this general solution, we're going to need its derivative. Look at the first boundary condition, get this relationship, which leaves us with this surviving function. Evaluate it at the other boundary condition. It says either b equals 0 or this parenthetical part equals 0. And the parenthetical part equals 0 when this is true, or when alpha equals tangent alpha. That's going to happen an infinite number of places. We'd need a computer to find all those places. There's not a nice closed form solution that comes up with them. But I'll call that the eigenvalue generating relationship. This thing right here. Alpha sub n equals tangent of alpha sub n. For all those positive integers. And here would be the, well, actually here would be the eigenfunctions, or these eigenvalues, where we have to use those eigenvalues. So we're plugging back into this function, but now with the alphas that satisfy this relationship. So here's one eigenvalue of 0 and its corresponding eigenfunction. Then we get an infinite number of other eigenvalues and their corresponding eigenfunction. So just so you at least kind of know what the alphas are that satisfy this, this is kind of a backwards chart. These are the tangent of alpha lines. So that would be functions corresponding to the right side of this equation. When the argument is just alpha itself, you get a straight line here. And every place that intersects all these lines, that's where your alphas are. Intersects there, come down here, and that's that first alpha. This chart is for, I think, just the opposite, where it was minus alpha n equals tangent alpha. This chart's for a different problem, but it kind of gives you the idea of what's going on with this eigenvalue generating, eigenvalue generating relationship. So here's the summary of the eigenvalues and eigenfunctions for that problem. And that's that. We'll go on to the next subject. in the next recording.